So the first question here is, what is MPI? I would say before we do this quiz, there are no trick questions, other than maybe one, but there are no stupid answers. I'm sorry. So really, if you get these questions, these questions are deliberately designed to promote discussion, and almost every answer I offer is other than this one, is a valid answer for a message. If I say I'm going to teach you message passing, almost every possible option I'm going to give you in all the questions is a perfectly sensible answer for a message passing system. However, what I'm asking here is what is true in MPI. So don't, if you get some of these wrong or whatever, don't worry, they are deliberately meant to be. So if I show the results, yeah. So some of the questions have more than one answer. So MPI is both the message passing interface, but is also a way of doing distributed memory programming. And you will see on some of the questions, you can select more than one answer in some of the questions. That was really just there as a next one. Let's do the next question. To compile and run an requires special compiler, special library, special parallel computer, special operating system. I'm going to disappear literally for 30 seconds just to get myself a glass of water, but I'll be back. Okay, so special parallel computer, special operating system, because all MPI requires is that you can run multiple processes. It's based on loading multiple processes, and any computer can do that nowadays with any, even a single CPU core machine can run hundreds of processes. Now, saying special compilers is a perfectly reasonable answer, because the way that MPI is presented to a user, it looks like there are special compilers. You type MPI-CC or MPI-F90 or MPI. However, they're not really special compilers. They're just wrappers to MPI is a library of functions, and you don't require a special compiler. When you type MPI-CC or MPI-FTN or MPI-F90, it will just be calling the GNU compiler, the Intel compiler, whatever compiler you have. So it presents itself for having special compilers, but they're not. So it's important to know that when you compile an MPI code, the compiler has no idea. When you do call MPI init, for all it knows, it could make your keyboard go beep. It has the compiler has no idea what you're doing in MPI. Okay, so I've initiated an MPI program. I've run it on. So I've written an MPI program. I've run it on my laptop. MPI run -n for my MPI program, and somewhere early on, it will call MPI init, and yeah, so that's what will happen. But what does that call? What does that call do? And again, as I said, none of these answers are all of these answers could have been true for various message passing systems in the past, but most of them anyway. But the question is, what does MPI? How does MPI work? Give me a few more seconds. Okay, so so a lot of people think it creates the 4 parallel processes, and there have been message passing systems which have done that in the past. However, actually, what MPI, as soon as you type MPI run, you have, hopefully you can still see my camera, you have 4 processes running. The operating system creates 4 processes, 4 copies of your program, and they will just run. But some point in the future, then they may actually be they will actually the MPI what this call does is it actually allows the processes to subsequently talk to each other. And I've got a little example here, which is actually quite, maybe it's fun, I don't know. I'll just quick going to go a different this is actually, I've got a window here, hopefully you can see it, which is actually the repository for this thing. If I do ls, ILS, but I can do MPI run -n to ls. All that does is the operating system says, I'm going to run 2 copies of this command called ls. And now I get 2 LSs, right? Not particularly useful. But that's actually, but you can see the MPI run creates those 2 processes. It runs, all the MPI run does is say, could you please run multiple copies of this program? And so, and you can that illustrates the explanation here. Okay, the next question is if I call MPI receive and there's no incoming message, what happens? So people are doing very well actually on this quiz. I mean, a much more higher percentage of people are getting the actually the correct version for MPI than would normally happen, which is good. But it's still useful to discuss these things, because even if you know the right answer, it's maybe not. It's also interesting to discuss why that is the right answer. Why does MPI behave as it does? And as I keep saying, if you don't know the answer, guess. I'd like to know what people think, because it's anonymous. I don't know who's answering what. So, okay, let's have a look. Okay, so most people got it right. The receive waits until the message arrives, waiting forever. The reason that the receive doesn't say there's no incoming messages, well, the question is how long would you wait for a receive? But this is the basic question. You know, you issue a receive and there's no incoming message. Then, well, you say, well, is there a mistake in the program or not? How long should I wait for till I complain? MPI assumes 2 things. It assumes that you have a well-written code, a well-written application, a correct application, but it also assumes there's no hardware errors. There's no fault tolerance in MPI. There have been systems which basically would report after 10 minutes, an hour, saying they've not got a message here, there's something wrong. But actually MPI assumes that you have a correct program and that all processes are aligned. So it's the fact that this is in some sense related to the fact that MPI has no fault tolerance. MPI basically just assumes you have a correct program. So this is starting to get more technical. If you call MPI synchronous send and there is no receive posted, which of the following are possible outcomes? And the analogy for synchronous send is like making a phone call. That's my sort of analogy. I think if you've been on my course. This is, yeah. Again, it's which of these are possible outcomes? There's not. I mean, there may be more than one. There may not. I've got a good response. I'll just wait maybe. Okay. So MPI synchronous send is like making a phone call. You phone somebody and you wait until the receive is posted. That's what synchronous means. Again, D is possible in MPI, but not with synchronous send. Now, actually, people don't tend to call synchronous send, but it is there. There is another send called buffered send, which is the asynchronous send. Again, which people tend not, but this is something we'll talk about later. But if you call MPI asynchronous send, you have B send, buffered send, and there's no receive posted, which is the following possible outcomes. And we will look at, in one of the early exercises, the performance of these various MPI calls them send modes. I said, if you don't know, I'm going to just get credit. Okay, so now what happens with MPI buffered send is it's guaranteed. So MPI asynchronous send is like sending an email or writing a letter. It's called buffered because it's a fire and forget. MPI takes a copy of it and sends it later on. So so the two possible outcomes are the message is stored and delivered later on. If possible, that's what you mean by asynchronous. It's a fire and forget. Here's a copy of my message. You know, send it in the future, and it's like posting a letter or sending an email. But the corollary of that is F. The sending process continues the execution regardless of whether the message is received. However, actually B is a possibility. When I first did this quiz many years ago, I didn't have B as a possibility. Oh, it was there as an option, but it wasn't marked as being correct. And so on. Can anyone think why B might be an error? I say to MPI, please send this message, potentially a very big message, asynchronously, and just send it off in the future. You know, I don't really care when it gets there. Why could the send fail with an error? I won't have a guess. Okay. Oh, well, it could. That you're right. It could, but that would be true for any send. So that's that you're right, Cameron. But I'm talking about specifically for MP. Let's assume that that everything's correct about the send. That the parameters are correct, and that in principle it could work. In principle, you've done the correct thing, but in practice, yes. So buffers be too small. Absolutely, Edward. So the nasty thing about B send, and again, a reason why people tend not to use it explicitly, is that you are mandating to MPI. I mandate that you take a copy of this message, and MPI might say, and actually in MPI it's a bit bizarre. It's up to the user to provide that buffering space. There's a nasty called that MPI buffer attach, where you say to MPI, I'm going to do asynchronous send. I'm going to do B send. Here's a megabyte of space to store them, or maybe it runs out. So you're absolutely right. The buffer, because you're mandating to MPI, I mandate you buffer this. You take a copy. It could run out, and that is exactly correct. Yeah. Now, what people actually tend to call is MPI send. So if you call a standard send MPI send and there is no matching receive, which are the following are possible outcomes. And we'll come back to we'll come back to the rationale for having these three send modes a bit later, possibly. But most of you will probably only have used MPI send, to be honest. And one of the nasty things about MPI is what MPI send actually does is slightly more subtle than you might think. Again, this is not an easy question at all. I only understood all this stuff because when I first joined EPCC and had to learn about MPI, there were people at EPCC who were writing MPI libraries, so I could go and ask them what the details were. But these are not obvious points, but they are useful to know. Okay, so right, so now what MPI, the behavior of MPI send is not defined in MPI in the sense that, sorry, MPI is allowed, so MPI S send is synchronous, you wait for the receiver to pick up. MPI B send is guaranteed synchronous. It's a fire and forget, the system takes a copy. Now MPI send is allowed to be synchronous or asynchronous. MPI can decide. So the rationale for that is don't tell MPI what to do. Say to MPI, I've got this message to send. You decide if you send it synchronously or asynchronously, if you buffer it or don't. So you might think, given that it can be synchronous or asynchronous, given that MPI send can be either S send or B send, then the correct answers here would be the union of the previous answers for 5 and 6. And that's true. If it decides that it's synchronous, the wait sends until the receive is posted. If MPI decides, oh, no, I'll send it asynchronously, I'll buffer it, it's D and F. But B, which is a possible outcome for buffered send, isn't a possibility here. So MPI makes a decision: shall I buffer this message or not? But why does that mean that B is not an option? I maybe not explained that very well. I mean, I've maybe slightly convoluted there. The point is that when you do MPI send, MPI looks at itself and says, do I have enough buffer space? In practice, we'll talk, yes. So what MPI will do is it will specifically only buffer the message if it has enough space, if it thinks it's the right thing to do. So although MPI send can be either buffered or synchronous, the possible outcome for a buffered send where you mandate the buffering is does not have enough buffer space. It says, well, I won't buffer it. Yeah. So it's that MPI takes advantage of this freedom you've given it to do either of the two things. I'll put the explanation up if people want to. I've just said all that stuff. So more MPI receive as a parameter count. What does this mean? This isn't directly related to what I'm going to teach, but it's just an interesting point of discussion. And it illustrates a few things about MPI, which may not have occurred to you if you've written relatively certain class of MPI, but if you've written certain styles of MPI program. Okay. So this is very interesting. It's not the size. It's not the size of the buffer in bytes. So MPI tries to be portable, and one of the whenever you start talking about bytes, it's a bit nasty. You're talking about, I know C programmers love malloc things, but you know, so it's not bytes, okay? So and it could be a lot of systems it is, but when you do a receive, you also specify a type. So MPI tries to talk in numbers of items, and that's largely for portability reasons. Okay. So again, other systems have used bytes. So the answer is clearly then B or D, the size of the incoming integers or the size of the buffer you reserve. Now, actually, technically, when you call an MPI receive, if you say you issue an MPI receive with 10 integers, what you're telling MPI is, I would like to receive a message, please. And by the way, as somebody got right, I have reserved enough space for 10 integers. Now, in many programs, that is also the size of the incoming message. So if you've only ever written programs where the messages are of compile time, you know what the message sizes are, which is often true for regular domain decomposition codes, then B and D are the same thing. But actually, technically, when you say you want, what you're saying is, I'd like to receive, if I do an MPI receive with count equals 10 and the type of integer, you're saying, I'd like to receive a message from this part of process. By the way, I have reserved enough space for 10 integers. So it's the size of the receive buffer, not necessarily the size of the incoming message. And therefore, there's obviously an obvious question is, well, what happens if the incoming message is larger than count? You say, I'd like to receive a message, please, and I've reserved enough space for 10 integers, and then the incoming message is 20. What happens? You may have seen this happen in practice, you may not, but it's interesting to think about what happens. So the reason that the count is not the size of the incoming message, but how much buffer space you have, is to allow you to write programs where you don't know what the message size is. Now, clearly you have to be able to, so that's the reason MPI says, look, there can be situations where you want to receive data from somebody and you don't know how much data there is. And therefore, that's why that flexibility is there. But let's have a look. So, so this is interesting. A lot of people say D. So the actual answer is A. The MPI is rather, I think if MPI were designed today, 30 years on from its initial, then some of these might not be, D might be, but what MPI says is, you told me to receive a message from this person and the incoming message is too big. I don't know what to do. It doesn't do C because MPI does try and be clean. It won't try and corrupt data. So that's why it doesn't do C. It says, that's why you provide a count when you do a receive, is tell MPI, look, this is how much space I've reserved, you know, and so it can say, well, the incoming message is too big, so what will I do? Only the first count, that's interesting. So if you have got a compute, if your model of MPI of message passing is a pipe model, where you have data flowing in on one side and flowing out the other, like sockets, then D would be a perfectly natural result. The problem is, well, not the problem is, MPI is based on matching. A message either matches or it doesn't. There's no sort of partial matching. If D were the correct answer, you would have to then issue another receive for the remaining of the message. Now, you could do that. You could say, you could receive in chunks. But that's not, MPI is a very simple model, actually. And it's related. Two messages either match or they don't. And if they match, they're received in their entirety, if possible. They don't match, then they're not received at all. So D is what you'd say, as I said, if you had more of a pipe socket model in your mind. MPI is based on entirety matching of message. And the question would be, if D were the answer, MPI would have to say, I received them, but you'd have a much more complicated polling setup, which might be interesting. The final one is, what happens if incoming message of size n is smaller than count? So I said I'd like to receive a message from another process. I've got enough space for 10 integers, and the message comes in and it's 5 integers. What happens? Being very on the ball, which is nice. Results. Okay, so the receive doesn't fail with an error because I said MPI is there are situations where you need to be able to receive messages where you don't know how big they are. For example, if you're doing a particle simulation, you're not doing a grid-based simulation. You have particles. You would have to you would want to send to your neighbor all the particles which were within some cutoff distance of your boundary. And so I'm saying to the other, could you please send me information, all the particles which are within 1 angstrom of your boundary, if I think about a molecular simulation. I don't know how many I'm going to get, so I need to be able to say, look, send them to me. So it is C or D. The only reason it doesn't do D, I think, you can think of a lot of reasons. But I think the main reason is efficiency. MPI tries to be efficient. If I said to somebody, could you send me some data? And by the way, I've got a megabyte of storage, and you received 1 byte. You wouldn't want MPI to go off and spend a lot of time zeroing 999,999 bytes. It's really for efficiency, I think. And there are situations you can imagine you'd want D, the behavior of D, for functionality, but it's mainly for efficiency. So I think the main thing is, the reason it's not A, it's a perfect natural thing to think that it's A, but it's not, is that MPI is allowed to, I want you to be able to receive messages of arbitrary size, or at least where you don't know what the size is in advance. Okay, so I issue a receive. I say to MPI, I've got 10 integers. Then MPI returns, so I know I've received a message. All I know technically is that the size of the message was less than 10 or equal to 10, because any message that came in which was 10 integers or less would complete. So how do I now, in some codes, you know, if you receive a message, you know its size. But let's imagine you don't know the size a priori. How is the actual size? So I've issued a receive. A message has come in. Technically, all I know is that the count, the size of that count I specified. Clearly, I'd like to know how many I actually received. How can I ascertain that? So again, it's not trivial at all. You may have done. Okay, let's have a look. So so MPI does have to be able to tell you to write a correct program. You could put it in the tag, actually. You could tag it, but that's not done automatically. So you could use the tag, but that's not automatic. The value of the count is not updated now. You could imagine it might be, but if you think about it, if you think of the process, the count is passed as a it's not a pointer. So again, that might be nice, but if you think about the C interface, the count is just an integer, and MPI actually can't update it. So it's stored in the status parameter. Whenever you do a receive, you specify two storage locations. One is the receive buffer where the data goes into. The other is the status, which is the metadata. So the data is received into the receive buffer. The metadata is received into the status. The metadata is things like where it came from and also how big it actually is. So you may never have done this, but if you need to know, it's in the status parameter. It might be nice if it updated the count, but given the prototype in C, it actually can't because it's passed by value, not by reference. Just a couple of things. Which of the following is true? And this is approximately true. Which is nearest to the closest answer? You do two consecutive sends of one integer or one send of two integers. We'll actually measure these things a bit later, just after the coffee break. But what do you think is true to a first approximation? Is sending two integers compared to sending two messages of one integer compared to sending one message of two integers. Let's have a guess if you don't know. Let's have a look. So okay, so the reason why I think you may disagree, I think A is twice as slow as B, is that for small, the data here is trivial. The data here is one integer. Okay, I mean that's just a trivial amount of data. So the entirety of the time spent here is what we'll see is called the latency, the overhead. So this is basically saying, does it? If I go to the shop, well, it's almost. If I go to the shop and buy, if I go to the shop twice and each time buy a pint of milk, yeah, how long does it take to do that compared to going to the shop and buying 2 pints of milk? When you're buying a pint of milk, assuming the shop is 10 minutes walk away, it's all dominated by the setup time. So here the actual time to deliver the data is trivial. It's all about packaging up and software overheads. Okay, so this is basically saying, delivering a message has an overhead. In this situation, the payload, the actual data size is trivial. It's 4 bytes. And so A is twice as slow as B. So the fundamental optimization in MPI is always to send a small number of large messages, not a large number of small messages. So another question. Okay. I'm now sending how many? One. I'm now sending megabytes of data. Okay. A large amount of data. If I send 2 messages of size 1 million compared to 1 message of size 2 million, what's likely to be true? Most people have answered, which is good. I'll just wait for. That's good. So actually, A takes the same time as B because here the data, the entirety, it's a bandwidth thing. It's basically you imagine you're saturating the interconnect, the link. Most people got this right, which is very good. The setup, we'll see the parameters later on, but the latency, the overhead of this call is trivial is small compared to the time it takes to send the data. And so all the time is in sending the data. I've got an analogy later on. So actually, A should take about the same time as B. So for you don't really it's dominated by the bandwidth, not the latency. It's taking the payload. So again, I've got an analogy later on. I don't want to labour the point, but we'll come back to and we'll see what the numbers are I've used extreme values here when we do the exercise after the coffee break. This is a couple of things I just want to, I don't know if you can see the whole question. I'll do them. Which of the following possible outputs from this piece of code? I've used welcome and goodbye, not hello and goodbye, because they have the same number of letters. Print welcome from rank blah, print goodbye from rank blah. What do you think? I've run it on 3 processes, not 1 and 2. And this is just a bit of fun, but it does actually illustrate a genuine point, which I'll talk about. As I said, if you don't have time to work it out, you can just have a quick guess, but most people seem to be having. Okay, I'll show the results here. Okay, right, I'll just show the results. So, people are correct. Mostly the A, C, and D are correct, but B is not a possible outcome. Now, can someone say why B? Why is B not a possible outcome? Just anyone sit in the chat. Anyone who. Yes. So goodbye before welcome. Exactly. So the point is that when you run an MPI program, MPI run, I said, launches the process, but it also does the MPI run launches the process, but it also grabs their standard out. So the print statements you see on your screen are coming from MPI run. MPI run is gathering the data from all these different processes and merging into a single output stream, which appears on a single file or on a single terminal screen. But so you have 2 processes writing data. The output from a single process will always be in order. Okay, so this will. However, they can be merged by MPI run in any interleaved or in anything. So the order you see on the screen, just because welcome from rank 2 appears before welcome from rank 0 doesn't mean that print statement was issued in that order. Who knows what happened between the print happening and appearing on your screen? But what you do know is that they will appear in order. A particular process output will appear in order. So all of these have welcome from a particular process before the goodbye, except for this. Now that makes debugging MPI programs quite hard. It can be quite hard to track down your input. And again, the order that print statements appear on your screen so people will often do a send and a receive, and they'll do prints, and they'll see, wait a second, rank 7's printed that it received the message before rank 3 printed it sent the message. That's impossible. Well, it's like sending postcards home from holiday. You know, who knows what happens between this print being issued on a computer somewhere in the back of beyond before the print statement actually appears on your terminal. But it is MPI run, which is the management process, which is collating all this input, and it doesn't do it on a character by character basis unless it's broken. Yeah, so individual print lines will appear as they are. This is a slightly subtle question, and I think actually I won't do these 2. These are very. I won't. Well, okay. Okay, let's do this. Apologies, I shouldn't just jump about. Let's do this question because we've got some time. This is. I put this in for a particular reason, but it's slightly tricky. But I think I say, do you agree with, because it's trying to illustrate a point here. Again, this is the quiz that I do normally at the end of my introductory MPI course. Maybe not that experienced, but it may seem a strange question to you if you're a more experienced programmer. it's really trying to illustrate the difference between message passing MPI programming and shared memory OpenMP programming in some sense. So yes, that's good. People are answering it. Okay, that's good. Thanks very much. So, okay. So yes, that's very good. So you've done that. People have got so what people who are new to MPI, and you guys obviously aren't, is they think that this loop makes the loop parallel. Okay, that the for loop is just parallel. Actually everything in MPI is parallel. Okay, everything happens on every process. The difficulty of the MPI is the opposite, is doing things in serial. So this, if you were doing an OpenMP, then you would be doing things like this, but it's not true. So in fact, exactly, the most important point here, I think, is C. The for loop is entirely redundant. Okay, every process executes this entire for loop. Okay, but rank 7, if you're running on 10 processes, rank 7, it executes this for loop 10 times, but only executes it when the rank is equal. In other words, this loop is entirely equivalent to print hello from rank. Rank j is 10 times rank. You do see some of the people doing this, and it's not an incorrect code, but it's showing they don't really understand the model. That basically you don't need to loop over processes because every process is executing every statement in the SPMD model. The final question I have is just a final thing. Again, I'm going to take a very quick break, but this is probably the one you think. So what's out for this MPI code? Apologies for Fortran programs and apologies for the formatting, but we're doing an all reduce of my rank into even sum on the even processes, and an all reduce of my rank into something called odd sum on the odd processes. Okay, and then they're differently. So, and the sum of the first 8 integers is 28. 0 plus 1 plus 2 is 28. But what do you think the answer is? And again, I'll be back in half a second. So if you don't know the answer, just take a guess. And this is the last question we have. I have to. It's the closest thing I have to a trick question. I have to say that was. But let's see. Okay, so okay, it's a trick question in some sense that it's written to make you think that the even sum is 12, which is 0 plus 2 plus 4 plus 6, and that the odd sum is 16, which is 1 plus 3 plus 5 plus 7. But that's not true. The answer is actually B. So can someone who answered B say why it's B before I don't worry if you got this. This is the closest thing I have to a trick question. Anyone who answered B, I want to say why it's B and not. It's all up, but all, yeah. Why is it writing everything? Yes. Okay. So it's doing like all process in the communicator, and the important point is the communicator is convoluted. So remember, MPI is a library. So actually, MPI doesn't know what line of code you called all reduce from. Okay. So let's think here. All the even processes are calling MPI all reduce. Okay. So let's say I'm rank 2. I call MPI reduce to my MPI library. MPI says, okay, rank 2 is calling all reduce, but it says, well, it's an all reduce across com world. That means that I'll have to wait for everybody to call it. Okay. And when rank 3 calls it from here, that matches. The MPI library has no idea that the all reduces came from different lines of code. So in fact, all we're doing is we're doing an, if we didn't have the else here, this would hang. It would be a deadlock because you're not calling it everywhere. With this, you're calling the all reduce on every process, the all match. You get the right answer. But it just happens to be the odd processes assign the answer to something called even sum, and the even process assign it to even sum, and the odd process to odd sum. So that, again, this is slightly contrived, but it does show you that when you do an all reduce across, an all reduce has to be across all processes, but it doesn't have to be called from the same line of code. It could be called from somewhere else. And MPI, actually, there's no way MPI can know where it's been called from, MPI being a library. Okay, so I hope you found that reasonably interesting. There's some strange matrix here of what people got, but given that you were anonymous, it doesn't really matter. So we're slightly behind schedule, but the next talk is relatively short, and so what I'll do is I'll give the next talk now. We might overrun by 5 or 10 minutes. I'll try not to, but then we'll recover it over the coffee break. Again, if there are any questions about that, please, we can chat about them later if you want, but I will now just do the first lecture, which should be up here. I'm losing the plot. Oops. So I'm trying to so I'm going to give a bit of the history of MPI, and then we'll have a coffee break. I'll come back. I'll talk a bit about how MPI is implemented internally, and then we will do an exercise. So hopefully you can see my. I can't get the laser pointer to work, but can you see? Hopefully, if I point, can you? The laser pointer doesn't work in this kiosk mode, but hopefully, I think you can see my cursor. Can you? Yeah, good. Okay, so I'll use that to point. Yeah. Great. So I'll give a bit history of the MP. I mean, it's a sign of someone who's getting old that like me, that we like sort of history thing. But I think it's useful to think about MPI, where it's come from, because it gives you some sort of feeling for why things might be as they are and what's coming up. So before MPI came out in the early 90s, there were message passing was an established parallel computing model, but whenever you bought a new computer, they got their own proprietary libraries. So you had to rewrite your program because it had a different way of doing message passing. There were some portable libraries, but they maybe only targeted a variety of particular systems or interconnects developed by academic groups for research, and weren't there to be used by general users. And also different libraries use different models for communication. For example, you had a method of sending a message between two processes, but you might say, well, is that synchronous or asynchronous? And they all had different definitions of that. It made developing applications very hard. Basically, what you had to do is you had to write your own communications module. You had to write, my send, my receive, my this, my that, and every time you port it to a new platform, re-implement that library using the lower level calls that are provided on the system. People got kind of annoyed about this. So as parallel computing really started to take off in the early 90s, there was a community effort to fix this. So there was a thing called the MPI forum set up, which is still active. It had representatives from many of the academic library developers, but also the vendors And this was good because as a user, you would like the MPI library to do everything. But as a vendor, you're going to have to support that, and you want to keep it as tight as possible. But the specification is very large for two reasons. It's very easy to keep adding things into a library. You just add more functionality. And also, there are lots of different communications models, probably too many, corresponding to various communication models supported by its predecessors. So that's why you have synchronous send, asynchronous send, or standard send, which could be either, because different previous libraries have those models in them. But a lot of the specification was driven by the library developers. The reason the MPI is designed, I mean, nowadays it may look at it as a very low level library, but it's still quite well insulated from the hardware. The idea is to leave a lot of scope for optimized versions on different hardware. So often you say, well, what does this MPI call do? You can say, well, I can tell you what it's defined to do from the standard. I can tell you how it's probably implemented, but it may not be done that way. And that's deliberate. Many aspects of the MPI specification deliberately allow different implementations the freedom to work in different ways. And this makes it easy to port or optimize for new hardware. However, you do need to be available. You need to be aware of this. And it's very easy, surprisingly simple to write an MPI application that works on one version of the library or one platform but fails on the other. So the behavior you see, if you have a corner case where you say, I wonder what MPI does here, and you run it on a particular platform or something, that may not be guaranteed. That behavior may not be guaranteed. It may be that it just happened to do that on that platform. And this is classic with MPI send, and we'll come back to that later on. The early API is an application programming interface. It's a specification, not a piece of code. And there are several different implementations, maybe not many. MPI was defined almost 30 years ago. And in fact, if you looked at an MPI program from the early 90s, you'd probably recognize it. It might look a bit old-fashioned, and also MPI hasn't changed that much. There's been a lot of extra bits tacked on. I shouldn't say added on, but it's basically been the same. Fundamentally, it stayed the same. So 1994, the basic MPI came out, which has all the things we're used to: send, receive, communicator management, collective communications. Then they revisited 3 or 4 years later stuff that they had omitted from the first one, which is parallel I/O, which I talk about in a different course. Remote memory access, that is direct read and write, not matching send and receive. I'll talk about that tomorrow a bit. They started to support a C++ interface where you could do object.send and object.receive. That's no longer supported. And they also had brought in dynamic process management, which allowed you to start an MPI program on 100 processes and grow and shrink it. That has died. So to be honest, the C++ interface is officially not supported anymore. If you're a C++ programmer, when you call the MPI, it is a C library. That's fine because the interface between C++ and C is well defined. But the specific C++ interface, which might be nice for C++ programmers, is no longer supported. However, if you've done any Python programming, MPI for Pi basically just copies the C++ interface and implements it in Python. How they've done it, or mimics it, I should say. But the dynamically growing and shrinking MPI process is not something which has proved useful, in my opinion. More recently, so basically 1997, for 10 years, not much happened. But in the mid-2000s, what happened was hardware tried to changed. So before 2005, 2006, a large parallel computer comprised a few hundred or maybe 1,000 single-core CPUs. However, when multi-core CPUs came around in the early 2000s, we had thousands of nodes, but each with, we started to have multi-core CPUs, and the total number of processors started to rocket. So people came back and started to fix MPI. MPI was never designed for that originally. MPI was designed for a few hundred single core processors. That was its design point. There's been quite a lot of effort. We'll talk about stuff done in, I say recently, 10 years ago, shows how old I'm. Neighborhood collectives and unified RMA model. I will mention a few of these things, but the major additions since activity started again in the 2000s with these neighborhood collectives I'll talk about, and this unified RMA model. It's a way of effectively doing shared memory programming a la OpenMP in MPI. I'll talk about that. And yeah, version 4, which only came out a year or so ago, has got persistent collectives, which I'll talk about, but they're mentioned. They're very obvious generalization, and partition points, what I won't talk about. But I mean, MPI, one of the big things they created the MPI+2 was something called one-sided communication. There's a bit of detail here, but the main point is that the basic message passing model requires the sender to do a send and the receiver to do a receive, and the messages match. In the one-sided model, which was introduced a long time ago, you can do direct reads and writes. So if you want to write directly to someone's memory, do MPI put. So it's like a send with no receive. If you want to read directly from somebody's memory, you do an MPI get, which is like a receive with no send. There's quite a lot of technicalities around it, which I'll come back to actually later on. I don't find this model particularly useful, but some of its terminology is required for doing the RMA model, which is more like OpenMP. I'll explain all this tomorrow. MPI+3 introduced non-blocking collectives. Previously, they're very to use, just like a normal collective, but you get a handle back. Neighborhood collectives I'll talk about. Some improvements to one-sided communications, and some new tools. This is not so interesting. Okay, there is a new binding for Fortran 2008. A few other bits and pieces, but the main thing was the C++ language bindings were removed. C++ started to take off as a language again, you know, maybe 15 years ago or so, and became much more complicated, a whole huge bunch of features, and trying to maintain with a burgeoning language like C++, what does MPI do in this? They just kind of said that we can't. C++ is becoming too big and complicated, so we will just support the C language bindings. So the C++ language bindings are removed. Again, we talked about the non-blocking. So basically, if you have an MPI all reduce previous to MPI+3, you call the MPI all reduce all processes, and you would only get the answer. So when that function returned, it was guaranteed the all reduce complete. They added non-blocking functionality to the collectives, which says basically you call an MPI all reduce. You're telling MPI, please start to do this global reduction, but return control to be immediately. I'll go off and do something else, and later on I'll wait for it to complete, and you get back a request object, just like you do from a normal non-blocking send or receive, and then you do an MPI wait later on. And there's various technical. This now allows you to have multiple collective communications outstanding at once, and there's various definitions about the ordering of them. I don't find these. They sound great, but in practice, we could discuss it. In practice, I don't find them particularly useful, for a bunch of reasons. However, they did introduce new neighborhood collectives, which are an MPI. I'll discuss this later on. But what neighborhood? So MPI all to all. If you call MPI all to all, every process sends to every other process. An MPI neighbor all to all says every process sends to all its neighbors. What do its neighbors mean? Well, this is if you define virtual topologies, and I'll describe all this in more detail tomorrow. It means all your neighbors in a virtual topology. And the reason why this is nice is that if you have a stencil-based computation, you have a regular grid decomposition, you maybe have in 3 dimensions 6 neighbors, up, down, left, right, forward, backwards. This allows you now to do halo swapping with a collective operation. So these neighbor collective functions are useful, and I'll describe them tomorrow. But I'm just going through the history of them at the moment. There were various changes to one-sided. Again, this is technicality. I'm not a massive fan of the MPI put and get. I don't find it useful, but they tidied it up so that it was more fit for purpose for what I am going to talk about more tomorrow, which was this RMA model. So there are two ways of exploiting. So modern computers are shared memory systems. Even my laptop here has four processors with shared memory. The standard MPI model completely forgets that. It says, look, I don't care if your two processes are on different nodes connected by a network or running on the same physical computer. There are now two ways to exploit the fact that two MPI processes might be running on the same, or exploit the fact that computers are shared memory, are multi-core shared memory nodes. One is hybrid MPI+OpenMP, I'll talk about tomorrow, and the other is this new unified memory model, which allows MPI processors to do direct read and write in the same way as you do in OpenMP to shared arrays. So I'll talk about this tomorrow, but there are basically two ways now to have shared arrays on a node in MPI. One is MPI+OpenMP, the other is this unified RMA model, remote memory access model, which I'll talk about tomorrow. Some selective features in MPI4, persistent collectives. It's always been a bit bizarre in MPI that if you call an all reduce on MPI COM world on a huge machine like ARCHER2 on 100,000 processors, there's clearly an enormous number of optimizations that the MPI could do on that. But there was no way of saying, look, I'm going to do this lots and lots of times. Go away and work out the best way to do it. So if you call 1 million all reduces in a program, every time MPI gets that all reduce, it pretends as if it's never seen an all reduce before. So persistent collectives are really useful. They say to MPI, look, here's a collective operation, and I'm going to do it lots and lots of times. It's going to be persistent with the same inputs, the same outputs, the same functionality. Please go away and find out the best way to do this. So this tells MPI, look, I'm going to do this collective a lot. Go and work out the best algorithm to do it. And I want you to spend quite a bit of time doing that because I'm going to call it trillions of times. So that was quite a sensible thing. There's also something called partition communications. I'm not an expert on, but it allows multiple contributions to a message before being sent. It allows you, for example, to elegantly pack a large MPI message from multiple threads. But I'm not going to talk about that, but I'm just thinking about what's going on. There is an MPI 5 ongoing. So I looked at the MPI 4 on web pages just the other day to see what they're working on. This is just there's a selected list. So application binary, the application binary interface. At the moment, MPI is portable, but only if you recompile. So what you're saying is, and that can be, that means if you switch MPI libraries, if you're on a computer that has two MPI libraries, one Intel MPI and one OpenMPI, you have to recompile your main program when you link to the new library. The reason is you say MPI com, you define a communicator in your program. MPI doesn't define what that is. So for example, one MPI implementation might store that as an integer, and then, or another one might store it as a pointer to some structure. And that causes you problems. So the application binary interface is a way of mandating actually how MPI is implemented, at least, and that allows you to switch MPI libraries without recompiling. And that's becoming, a lot of people, that would be a useful thing to do. It would allow you to have a pre-compiled program which would run anywhere, regardless of who. And that there's some progress being made. Fault tolerance, I don't think will ever happen. I think it is. I don't believe it's possible to institute fault. So fault tolerance is saying what happens if I'm running on 1,000 nodes of ARCHER2, which is 128,000 processes. One of my nodes, one of my computers dies due to a hardware or software fault. Currently, your MPI program dies. This is saying, how can you make your MPI program tolerant to hardware failure? I personally don't think that's worth it, but we can discuss that. Hardware and virtual topologies. Hardware is becoming more complicated. You now have nodes are very complicated. You have hundreds of processors with very, very complicated cache hierarchies. You now have accelerators. So some nodes may have GPUs and CPUs, and in the future may even have additional types of processor. So this is basically saying, how can we make MPI aware of the fact that modern hardware is complicated? So you might want to know, am I running on a CPU or a GPU, things like that. I guess it's related to hybrid and accelerator, hybrid program runners accelerators. Languages, they're looking at, there has been an effort to implement MPI. You can call MPI from Python using MPI for Pi, but that's kind of that's just a one developer project, and it's quite scary actually that millions of lines of code written in Python that call MPI rely on some library that somebody may or may not support. So that they are thinking about, I believe, having official MPI. Officially, MPI is only supported for Fortran and C at the moment, and C++ by implication, because C++ can call C. I think they're looking at supporting Python. Remote memory access is, again, although we have these MPI put and MPI get, which allows you to remote read and write between distinct processes, the performance tends to be bad. I think they're revisiting for the second or third time how to fix that. Sessions, I didn't need to leave in there. Sessions is a technical thing. It all comes down to the fact of whether you have an MPI process which has a rank, and you have an operating system process which is a physical process ID. Should they be the same thing? It might be more sensible to say in a multi-threaded environment, well, every thread on my program is a separate MPI process, even if it's not. I believe that's what they're doing there. I didn't actually need to put that in there because I've not really looked at that. If you're interested, you can look at the pages for a complete list. So just briefly talk about implementations. There are many different implementations of the MPI library. Many of the early ones were built on existing portable libraries. People had their own message passing library, and they just put a layer on top which interfaced it to MPI. Really, there's two main open source MPI implementations just now, MPI-CH and OpenMPI. Many of the vendors are now based on these. So for example, Cray MPI, which you get on ARCHER2, is based on MPI-CH. I think Intel MPI is a completely different port, actually. I'm not entirely sure about that. But there are two main open source MPIs, MPI-CH and OpenMPI. There are vendor ones. Microsoft used to support Microsoft MPI. I don't know if they still do, I have to say. But Intel MPI is one you may come across as well. This is one of these rock family trees. We haven't kept, it's very out of date. This only really goes up to the 2000s. But pre-MPI, there were lots of things. EPCC had a message passing called Chimp. Los Alamos has something called P4. Ohio has something called LAM. Oak Ridge has something called Parallel Virtual Machine. These guys sort of came together to do OpenMPI and MPI. But really, the MPI-CH2 and OpenMPI are really the two main open source libraries at the moment, open source implementations of MPI. MPI-CH is sort of the default MPI. It's very mature. I believe it supports up to MPI-4. There's good support for generic clusters. And I said many vendor MPIs are now based on MPI-CH. What HPE do when they say we've got this massive machine called ARCHER2, and it has a bespoke interconnect. It has the slingshot interconnect, which is not a proprietary interconnect. It's bespoke. It's not like InfiniBand. It's how do we have an efficient MPI to run on slingshot network? Well, they take a portable MPI like MPI-CH and optimize various bits. The name is now MPI-CH. And how do you write an MPI library which can run on any hardware? Well, what you do is they have a concept of an ADI, an abstract device interface. They have a very low level set of functions called the ADI functions, which do very low level things, send n bytes between process A and process B. And basically, what HPE will have done to optimize MPI for ARCHER2 is they have rewritten this lowest level thing using hardware specific things on ARCHER2. So what you do is you say, you know, I have a very 99.9% of your library is completely hardware neutral. You have a very small number of low level functions which do very detailed things, and you say these things need to be implemented for this particular hardware. So it makes porting the library relatively straightforward. OpenMPI, that's what I have on my laptop. It is very active. Originally, so it has special emphasis on support for InfiniBand hardware. That was one of its original design goals. Originally, it was a lot of people used OpenMPI to look at fault tolerant. Again, it's an open source project with large and varied community effort. I don't really have any opinions with OpenMPI and MPI+CH. I really just use whatever's there. The main thing I would say is if you have a correct MPI program, it should run on every MPI implementation. You shouldn't really care if you're running on which one. It may affect your performance, but it shouldn't affect your correctness. So summary, most MPI implementations use a common superstructure, lots of lines of code to deal with very high level things, and they'll implement a number of different ways of sending data, and we'll talk about in the next lecture. But all hardware-specific code is kept separate from the rest of the code, hidden behind some, and MPI+CH equals an ADI, an abstract device interface. And so if I were to tell you to optimize an MPI library for a particular architecture, you would rewrite the low-level communicating function in the ADI. You would look at the collective. There's nothing to mandate. There's nothing to mandate the collectives have to be implemented in MPI. Your network may have modern networks may be able to do all reduces in hardware, and so you would optimize the collectives and use machine-specific capabilities to an advantage. As we said, the MPI model talks about processes sending and receiving data, and other than a few places we'll maybe touch on, really doesn't define whether those processes are on the same computer in a multi-core setup or on different nodes or a distributed memory system. But however, under the hood, modern MPI libraries are aware of shared memory nodes. So we will see when we do performance measurements, it's much quicker to send messages between the two processes on the same node than between different nodes, because MPI is optimized for that. So the abstract device interface will have multiple implementations. It will do things differently, saying, are these two processes on the same node? Yes, I can do clever tricks. I'm just trying to say that modern MPI implementations are very aware, although the library to the user, you don't care often whether two processes are on the same node. The implementation is aware of that and will use it to optimize where appropriate. So that's us sort of on track for the coffee break. If I look at the timetable, I don't know if anyone has any questions they'd like to post, but I'll check the timetable. I should have up somewhere. Yeah, so we've got a coffee break now. We'll come back. We'll come back at 11:30, and this whole session is on point-to-point performance. What I will do is I will talk about the way MPI libraries are implemented, in particular, the way that send and receive might be implemented under the hood. And then we have an exercise, which is a ping-pong exercise, which can tell you surprisingly large amount about performance. So I'll talk about maybe 3/4 of an hour talking about point-to-point performance in terms of how MPI libraries are implemented, and then we'll have an exercise, and that'll be our first chance to log on to ARCHER2, and I hope we'll sort out any niggling issues about ARCHER2 access at that point. It's all pre-packaged, it's just compiling and running the program, but it's quite a lot of things you can change, and you should be able to. I think so. This will give you a number of insights. One is, how long does it take to send a message? A microsecond, a millisecond, a nanosecond? What's the bandwidth? A gigabyte a second, 100 gigabytes a second? What's the difference between on node and off node? Numbers will be specific to ARCHER2, but the general concepts are generic to any modern parallel computer. So we'll come back at no. I typo. 11:30 BST. So have a break, and I'll see you then. If you have any questions, I'll maybe look at the Etherpad page. I'll leave that back up again, which a lot of chat, which is good. I'll maybe leave that up, and I'll have a look at that when we come back. I'll leave that up, and I won't just. Okay, so I'll just get the next lecture up. I said what we're going to do is this session is on point-to-point performance. So between now and one, a lecture, and then a practical, which I'll describe when we get there. Just see if I have my slide up. I don't. Sorry, I'm slightly disorganized as ever. Okay, so I'm just slightly. Right, so hopefully we can see that. Yes, okay, I'll get my chat up here. So, as I said, MPI libraries are free to implement things however they like, regardless of, as long as it respects the specification. But this is sort of a mental model of how things work. And in some cases, there's a bunch of different things in this lecture. But whenever I talk about what the MPI library does internally, it's a useful model for what they probably do. But there aren't any guarantees unless you go really look at the source code. But we'll see hopefully when we do the ping pong exercise that it is a useful model. We'll talk a bit about the library structure. I've covered some of that already. Point-to-point collectives, and actually at some point I've trimmed this lecture down to actually the group communicators and single-sided. I think I probably pushed it on later, so I think the apologies for that. So actually I also need to. Oh, I've kept recording. Okay, so we're still recording this. So as I said, like any large software package, MPI implementation needs to be split into modules, and actually the way that people write them, actually there's quite a natural mapping between the chapters of the MPI standard and the way you write your library. So there's the MPI standard is point-to-point, collectives, groups, contexts, communicators, process topology, such like. But we're going to be talking really here about how point-to-point is probably implemented. As we said before, there may be these hidden internal modules. The most important one being the ADI, the abstract device interface, that actually is the lowest level thing. Below that, you go down into more hardware specific things, the way the networks work and such like. So point-to-point of most MPI implementations. We've talked about how MPI has in the quiz these has more than this, but the three basic high-level point-to-point calls: MPI+ send, which is guaranteed to be synchronous, like making a phone call. You wait till the receiver picks up. MPI+ send, which is guaranteed to be asynchronous, like sending a letter, or buffered, which is what the B means, but the user has to provide the buffering space, and that's a bit awkward. Or MPI send, which is probably what most of you have used, which MPI has the implementation has the option to do it synchronously or asynchronously, but in practice, what it will do is it will send small messages as asynchronous, buffered messages, and large messages as synchronous. And we'll talk about that a bit longer. Collective calls are usually, but not always, built from point-to-point calls. I mean, you may be able to circumvent them in certain. That will be the default fallback implementation. But for example, you may have a clever network which can do an all reduce of a double precision 30-point number, for example, in which case in the library you'd shortcut that and call that directly. I'm not talking about MPIO here. I have a separate sort of course on that. But MPIO is usually built on standard communications libraries. If you don't have to write your own MPIO, almost all libraries use the Romeo implementation, which is built on standard MPI calls. There's a large number of point-to-point calls, but these can often be built from a simpler set of core functions, and we'll talk about that and how that impacts performance. So you may be obvious to you, but I think it's worth talking about it. I'm not a massive fan of cars. I mean, but I think they're actually a very, very useful analog for a lot of things in computing and message passing. And so, you know, we're gonna do a ping pong exercise where we send a message between two processes repeatedly, so we can measure how long does it take to send a message of 1,000 bytes, how long does it take to send a message of 1,000,000 bytes, and then we're going to try and understand the graphs we get out of time against message size, for example. What's our performance model? Well, I think car journey is a very natural analogy. So my car's parked in a nearby garage, so it takes 5 minutes to walk there. Okay? After that, I can do an average of 60 kilometers per hour, or for those in the UK, that's about 38 miles per hour when driving. So how long does the journey take? What's my average speed? Well, how long a journey takes is there's an initial overhead of 5 minutes, okay? And then every time I go 60 kilometers, it takes me an hour. So that's it. So the graph of time for journey against distance is linear because I'm assuming I'm doing a constant speed. But importantly, it intercepts at a non-zero value because there's a startup time. So any journey takes 5 minutes, at least, then longer journeys take a longer time. And if I plot this on a log plot, which we tend to do, because what we're going to do when we run our ping pong example is this will be the time for the message. This will be the size of the message, and we'll tend to double it up. So when we plot it like this, you see that it looks like, you know, a flat region, and then it zooms up. It's actually linear. But this, you know, this is an interesting graph. This is the kind of graph you would probably plot if you were measuring this in reality. So there's very different small and large distance behavior. Okay, for small distances up to, you know, a few kilometers, they take constant time. Okay, because for small distances, I'm not driving for a long time. I'm spending most of my time walking to the garage. So again, very different small and large distance behavior. For small distances, we get a constant time. For large distances achieve a constant speed. So if I plot the speed, not the time, but my average speed, for small distances, my average speed is very low because I have this 5 minute overhead. But for large distances, I go up to a constant speed of about 60 kilometers per hour. So there's clearly a small distance and a large distance behavior. And for small distances or messages, we would typically plot time. for large distances, we would plot speed, which will turn out to be megabytes per second or bandwidth. What I mean by small or large? Well, there's a number called n.5. It's a useful number it's a characteristic of my car, also it's a characteristic of a network. Imagine that you have, at what point do you spend equal time driving as walking? Okay, well, that is if I travel n.5 is your speed when you're driving times the overhead of getting to your garage. n.5 is 60 kilometers drive times 5 minutes is 5 kilometers. In other words, if I travel less than 5 kilometers, I spend more time. I spend more time walking to the garage than I do driving. If I travel further than 5 kilometers, I spend more time driving than I do walking. So, and you can see that 5 kilometers is roundabout, yeah, where you see this transition between, about 5 kilometers where you see it taking off, or here it's where you see it flattening out. So when I say, what's a small distance, what's a large distance for traveling by? So basically, if I was traveling less than 5 kilometers, it's not worth driving. Above it is probably worth. So that there's this transition point, which is the overhead times the speed. And when we actually talk about networks, that will be the latency times the bandwidth. It's a useful number. And I say small messages, large messages. What do I mean by small or large? It's useful to get some ballpark feeling for what that is. But for this model, it's 5 kilometers. So we have a simple constant overhead, then constant speed model. And we have this parameter, which is the overhead times the speed, which gives us some feeling of when that flips between small and large distance behavior. For point to MPI, the latency is the overhead sending any message. Now, you have to be careful here because people from a computer science background tend to use latency as being the total time taken for a message. That's not what we mean here. Latency is the overhead of sending any message. So it's the time to send a very short message, which in practice is the time to get a short message onto the network. And we will see that those numbers are in the microseconds, hopefully. So that's the equivalent of our how long does it take to walk to the garage. I want to travel anywhere. I want to send any message at all. And actually, that turns out in modern computers to be very much a software overhead. It's because it's actually a software overhead, typically. The bandwidth is the rate of transfer on the network for large message sizes, e.g. 10 gigabytes per second. So if I plot those numbers with a 10 gigabyte per second bandwidth, I see this is my speed versus the time versus message size. It splits up at about just around about 10 kilometers. It starts to go up again. Here we start to see a flattening off roundabout. And if I told you to where the cutoff point was, you'd probably say for this system, 10K is about the switchover point. Below 10 kilobytes, they're small messages dominated by the latency. Above 10 kilobytes, you're dominated by the bandwidth, and you tend to get a constant bandwidth. And actually, if we work out n.5, 10 gigabytes per second times 1 microsecond is 10 kilobytes. So this latency bandwidth model is very useful as a first approximation. But in fact, we'll see that in fact things as ever are a lot more complicated than like this. If you plotted your real time to get to work against the distance, it wouldn't be like this. There'd be lots of other things going on, congestion and all kinds of things. But it's a very useful first stop model. So the first thing you ask when you get a new machine is, what is the latency? What's the bandwidth of message passing between two processes? So we'll come back to that, but for the moment, MPI, we've talked about multiple types of send. We've talked about buffered already. Buffered sends complete locally. In other words, the call returns to you whether or not a match and receiver is posted. The data is buffered somewhere until the receiver is posted. I've said in MPI, it's rather nasty. It's up to the user to supply that buffering. Buffer send fails if insufficient buffering space is attached. The routine is called MPI buffer attached. Again, people in practice tend not to use buffered send, but synchronous send can only be complete when the matching receiver has been posted. In that sense, the buffered send is like sending an email or a letter. Synchronous is like making a phone call, waiting for someone to pick up. But also there are other send. There's actually a ready send. So what a ready send says is a ready send says, I guarantee when I call this send, I guarantee that there is already a receive posted. Now, if you know that, clearly it's then quicker to send the message because you assume David's just called ready send. This exists in MPI. You should never ever use it. It's there for historical reasons. But you're saying, I know this, so I can just put the data over. If the receive hasn't been posted, then all bets are off. This is clearly there for historical reasons. Clearly, when MPI was defined back in the midst of time, somebody said, oh, you should never use it. But I just mention it here for completeness. The interesting one is standard send. Standard sends may be buffered or synchronous depending on the availability. Now, in practice, the MPI standard says, the MPI documentation says standard sends can be buffered or synchronous. You don't know. So every Monday, Wednesday, and Friday, they could be buffered. Every Tuesday, Thursday, and Saturday, they could be synchronous. And on a Sunday, it could flip a. In practice, that's not what's done. It is possible. In practice, what MPI says is it will depend on the availability of buffer space and which mode the MPI library considers to be the most efficient. So basically, in practice, what MPI says is, for small messages, I will buffer them. For large ones, I won't. And that's basically, and we can try and see those thresholds when we do our exercise. So there is a number of things which MPI defines about messaging, which you may not be aware of. MPI requires the following behavior. Ordered messages, now this is interesting, messages between two endpoints must be non-overtaking. So so what it means is that MPI remembers the order that messages were sent in. And so the technical statement is, if you issue a receive and there are multiple messages, let's think of having in your inbox, multiple outstanding messages which match that receive, they will be received in the order they were sent. That's actually quite a lot of effort to achieve because at the hardware level of modern networks, messages aren't ordered. When you send a message, it's split up into multiple packets. The packets will be routed independently and reassembled at the other end. But actually, it's very important. Most MPI programmers assume ordering of messages without realizing it. So, for example, if you have any situation where you send some data, and then send a message saying, "Oh, by the way, that a kill message. Could you stop now?" Yeah. If the kill message overtook one of the data messages, your program wouldn't work. There's a surprising number of situations where you assume message ordering. If message ordering isn't guaranteed, it's actually quite hard to write correct programs. You end up having to tag every message and match the tags. So, fairness in processing, MPI does not guarantee fairness. What that means is, if you do an MPI, if you have a lot of outstanding, if you do an MPI receive from MPI any source, okay, so I'd like to receive a message, I don't care who it's come from, you would hope that MPI is fair, that it takes them sometimes from rank 0, sometimes from rank n. That's not guaranteed. It could always take, if you do an MPI receive from MPI any source, MPI might always receive from the lowest rank. But in practice, no. Most implementations try to do this to keep things balanced. Resource limitations. There should be a finite limit on the resources required to process each message. This is why. Now, you might actually like all to be asynchronous. You might like to say, look, whenever I issue a send, the problem is if that send is synchronous and there's no receive posted, I wait, which is a delay, and I may wait for a long time. I may wait forever. Wouldn't it be nice if all sends were asynchronous? Every time I issued a send, MPI took a copy of it and guaranteed and delivered it later. So your life would be easier if all sends were asynchronous. However, MPI cannot guarantee that all sends are asynchronous because you might be an arbitrary number of outstanding messages. It's like posting thousands of postcards into your thousands of Christmas cards into your post box. Eventually, the post box is going to fill up. So there are various things which mean that MPI can't do what you want. But there is a technical statement that MPI implementation should place a finite limit on the resources required to process each message. The final one is progress. I've got some examples of this, but this is something which is slightly subtle, but it's important to be aware of. Outstanding communication should be progressed where possible. What this means is when you, I'll come back to, one of the models, your model of MPI is a universal postman or postwoman, that basically it's running all the time. And when you ask for MPI to deliver a message, it picks that up and delivers it. But actually, MPI is probably implemented as a library. So actually, the only time MPI can do anything is when you call the MPI library. So when you're not within the MPI library, it's unlikely that MPI can do anything. So what that means is you might think that MPI is continually interrupting and keeping things ticking along. Most implementations aren't like that. What most implementations do is, whenever you call any MPI routine, the first thing they do is they go away and use that as an opportunity to keep things moving along, to look for, are there any incoming messages that haven't been processed, any outgoing messages that need to be sent. In some senses, every time you do an MPI call, MPI treats it like a manual interrupt and goes away and does something. And we'll talk about the implications of that later on. These influence the design of MPI implementations, obviously. So here's message progression. It's slightly contorted, but you might think that when you do a barrier, okay, when you say everyone wait, everyone just sits there and waits, but that would cause MPI programs to fail. If you think about this situation here, okay, rank 1 is setting up a non-blocking receive from rank 0. Okay, so rank 1 is saying, when a message comes in, then please progress it. Okay, and let's assume that then rank 1 has said I want to receive a message from rank 0 in a non-blocking way. So it's set up, it's waiting to receive the message. Okay, and then rank 1 immediately goes into a barrier and sits there for rank 0 to appear. Rank 0 is saying, I want to synchronously send a message to rank 1. I'm not going to progress until my message has been received. So if all rank 1 does is sit in this barrier and ignores rank 0, then your program will deadlock, because rank 0 is sitting there saying, I'm waiting for rank 1 to call the barrier, but rank 1 is never calling the barrier because it's saying, I'm waiting for rank 0. Rank 1 is sitting on the barrier waiting for rank 0 to call the barrier, but rank 0 is expecting rank 1 to receive its message. So actually, what is actually happening is in this barrier, rank 1 is not sitting on the barrier. It's basically going, has rank 0 entered the barrier? No. Is there anything else I can do? Oh, I've got an outstanding I received. Oh, there it is, and it matches. So MPI is basically, whenever it's in the library, doing more than you think it is. Because if it didn't, then this is a perfectly valid program, then this would deadlock. So MPI is not allowed to just sit in this barrier. It has to progress, keep progressing outstanding communications, which in this case is keep an eye on this outstanding MPI I receive, which will then allow rank 0 to complete and then carry on. So again, this is slightly contrived, but also if you look at a lot of programs, this has to be true. You might say, why isn't MPI a multi-threaded library? Why doesn't MPI have a, so there's a concept in MPI of a progress engine, which basically keeps things moving. And what happens is MPI is manually calling that. You might say, why doesn't MPI have a separate thread? You know, a little thread which runs all the time and keeps things moving on, keeps things progressing, as you would probably expect if you were a network person. If MPI were designed today, that would probably be true, but MPI was designed 30 years ago when threading, when some CPUs couldn't even do multi-thread. CPUs were strictly single-threaded, and it's one of the problems with MPI, and we'll talk about this when we talk about MPI+OpenMP, is it doesn't really work very well with threading. It's a shame. But if you designed MPI today, you would probably say MPI would kick off at MPI init a little thread, which will keep spinning around and every now and again keep things ticking over, call the progress engine. That's not the way most MPI implementations work, because it's difficult to do that in MPI, and most of them were written a long time ago. So we'll talk about that a bit. MPI defines both blocking and non-blocking. A blocking call, if you do blocking synchronous send, MPI send, it says wait. I will wait here. I'm just checking I've got my camera on. I'm doing gestures. Yes, I will wait here until the send completes. If you do a non-blocking synchronous send, you say to MPI, please send this message in the future. I will come back later and check whether it's arrived. Non-blocking is very important in real MPI programs to avoid deadlock. Actually, at the very lowest level, the network protocols are probably non-blocking. So this allows it. So while your application may be blocked by the MPI library, you're saying I called synchronous send. My application is blocking until that synchronous send is received, or until someone has picked up the phone. Actually, within the library, it's probably done that in a non-blocking way and keeping things progressing on. So actually, blocking calls are often at the hardware level mapped onto a pair of non-blocking send, receive, and await. It's just a if you're a networking person, you may be aware of how these low-level protocols work. So here's a point-to-point example, which uses standard non-block communications. Okay, if this was so I've got a standard, and I've got an example program for tomorrow, which is like this. I've got a standard neighbor. There's a typo on this. I've updated this slide. Oh, sorry. I've updated this slide, and I have not spotted a typo. Sorry. So sorry, I'm getting very strange behavior here from my mouse. Okay, my mouse disappeared. Sorry. Yeah. So if you had blocking receives here, MPI receive from your up neighbor, that would guarantee the deadlock, because every process will be trying to receive from their up neighbor, which requires there to be a send from the down neighbor, and that would never happen. So if you want to do even simple boundary exchange with neighbors, then you need to use non-blocking examples. So what you do is you say, I will set up a receive from my up neighbor, but please return control to me before that happens. I will set up a receive from my down neighbor, okay? Please return control to me. And you get these tickets back, these requests from MPI. I've called request 0, request 1, these identify that communication. I can then send to my down neighbor, which will map the I receive to the up neighbor from my neighbor. I can then send to my up neighbor, which will map this down. And then I have to wait for these receives to complete. Okay, so this is the standard way of doing Halo exchange. This is a 1D example. It generalizes to 2D. Actually, though, this is something that people do get wrong. This may look a bit unnatural. MPI receive up, MPI receive down, MPI send down, MPI send up. The natural thing would write I receive up, I receive down, send up, send down. Can anyone think why you need to have, for a correct program, and people often get this wrong, you have to receive up, receive down, send up? It's an unusual situation where this is an issue on small numbers of MPI processes. Normally, you get issues on large numbers of MPI processes. I don't know if anyone can think of an issue there. Yeah, so why do sender and receiver need to be swapped? So they are swapped, but in most cases, if I was running on 100 processors, yeah, this code would work if I did MPI receive up, MPI receive down, then I did send up, send down. It would work, okay? But there's something special, bizarrely, on small numbers of processors that makes this go wrong on small numbers of processors. The point is that when I do this, I receive from an up neighbor, okay? I'm saying I want to receive a message from my up neighbor. In the normal case, you only have one up neighbor. Only that person is sending to you. So if you've got 100 processors and I'm process 8, okay? I'm saying I want to receive a message from process 9, yeah, which is my up neighbor, and I want to receive a message from process 7. That's my up neighbor. I'm rank 8. The up neighbor is 9 and that's 7, and there's no ambiguity there. But imagine I'm only running on 2 processes, 0 and 1, and I've got periodic boundary conditions, which is often the case. If I do my up neighbor and my down neighbor are the same. So I've issued a receive from, if I'm rank 0, I've issued a receive from 1, from rank 1. I've got 2 receives from rank 1, okay? And so if I have these sends in the wrong order, then the send up will receive the receive, which will match. Now MPI remembers the order. So when I do this send down, okay, if it matches multiple receives, which it can do with period, it will match the first one which was issued, which is this up neighbor, and then this send up will match this receive down. So the ambiguity comes when your up and your down neighbor are the same person. Then you need to be careful about the ordering, and that's not obvious immediately. But I have seen cases where this is the. You might say, well, I'm never going to run on that few processes. But if you've got a 3D program, 3D decomposition on 8, even on 32 processes, you could be on a 2x4x4 grid. So even on 32 processes or less, you can get this ambiguity. You can also fix this up by tagging the messages. You could have a different tag for the up and the down send, but message order preservation is the right way to do it. It's the elegant way to do it. The reason I've got that example is that MPI also defines persistent communications. So what you say is they're like non-blocking, but they can be run multiple times. What you're saying is, here's a send operation. I'm going to do it lots and lots of times with the same in buffer, the same out buffer. And what that allows MPI to do is that the argument checking, or any checking it does, needs to be only done once. And so therefore, a persistent communication is set up once and then activated many times. Now, in principle, that allows MPI to do lots of optimizations. In practice, for point-to-point communications, there's very little optimization you can do. But for collectives, there's lots of optimizations you can do. And so persistent collectives are included in MPI for that reason. The optimizations you can do in collectives are MPI might want to identify all the processes that are on the same node and do some clever shared memory tricks. That takes time to analyze. So basic for collectives, it can analyze the collective pattern once and decide the best algorithm and then issue it many times. Without persistence, it has to analyze the behavior every time. And in practice, there's not enough time to do that. But the way persistence work is you say, I'm going to initialize a receive from my up neighbor. I'm going to initialize a receive from the down neighbor. So this request now doesn't refer to an ongoing communication. It refers to the communication you might want to later start. So these requests are overloaded. They're used for multiple different things. You can MPI sending it to down neighbor and sending it to an up neighbor. So now MPI said, look, in the future, I'm going to want to issue this receive call, this receive call, this send call, this send call. You remember them as requests 0, 1, 2, and 3. And I do MPI start all. This says now initiate all those in a non-blocking way, and then wait for them all to complete. So this is the way. It's like non-blocking, but you have a setup phase which initializes the communication. Then you have a phase where you actually issue them. The ordering of individual calls is not guaranteed. So MPI has the freedom to initialize. So you do have to worry about tagging here. So that's a bit of an issue. There's also derived data types here. I saw somebody did mention in the chat about derived. I'm not going to talk a lot about derived data types here. The most common use for derived data types, though, is a standard MPI send has a buffer and a count. You can send 100 integers, but in many situations, it actually the data is not contiguous in memory on your application. The classic thing is a multi-dimensional halo swap. Most of the halos will be non-contiguous data. You could do a copy in, copy out, but MPI has a set of derived data types to define a single data type which has effectively corresponds to strided data. They're called vectors or subarrays. Under the hood, MPI is probably doing a copy in, copy out, but it is definitely worth using these for those cases. So the thing I wanted to concentrate most here is the thing about protocol messages. All the MPI implementation need a method for delivering packets of data to a remote process. The These could be actual messages, or they could be headers, flag messages. Okay, so this is a model of how MPI implementations do things. Whenever a process sends an MPI message to a remote process, an initial protocol message IPM must be sent. So your model is, when I call a send to another process, I send a little flag, a message saying, I want to send you some data. Okay, so you've got, think of it, and it'll probably be of some fixed header size. Let's think of it being 128 bytes, for example. So whenever you call an MPI send, what MPI actually does is it sends over initially a little protocol message of 128 bytes saying, I want to send you some data. Please get back to me later. Now, it may also contain some data. We'll come back to that, but that should be your model. The first thing MPI does is send off a little acknowledgement saying, I've got some data for you. And typically they use fixed size headers for all messages, and 128 bytes might be a standard size, say 256 bytes or something like that. So I've said I want to send you some data. If the receiving process has already issued a matching receive, okay, then the receiving process can say, well, he says that he wants to send me some data. Oh, there's already an outstanding receive, and it can match them up. If not, the data comes in, the MPI will say, well, that person wants to send me some data, but I don't have a corresponding receive. I'll park it. So that's called a foreign send queue. Okay, that's incoming messages which have been sent from somebody, but for which there is no longer a matching receive. There's not yet a matching receive. And similarly, when you call a receive call, you say, I want to receive some data. Okay, you would immediately say, well, I want to receive some data from that person. Maybe they've already contacted me. I can process it now. No, they haven't. It has to be stored in the receive queue. So, so in principle, there could be many such queues. That's a technicality, I guess. The main thing that this tells you is, and this is unfortunately hard to realize in practice, but you should issue your receives early before the sends, because if a receive is already posted when the send comes in, it can match quicker. So issuing receives early is a technique which is in principle good, but in practice we'll see it's quite hard to do. And then there are different message protocols. Typically MPI implementations use different underlying protocols depending on the size of the message. And the two ones are eager and rendezvous, and they match very much onto synchronous and asynchronous. And so there's many variants of these, but what we'll do in the exercise is to try and ascertain experimentally from measuring message times when MPI switches from the eager protocol to the rendezvous protocol. So what is the eager protocol? Well, basically says, whenever you send your initial header message, you also send the data. Okay, you say, I'm wanting to send you some data, and here it is. Okay, the initial protocol message contains the full data for the corresponding MPI message. Now, clearly that could only be done for small messages. Okay, what you're relying on here is saying, when I send the data to somebody, I know I'm sending a kilobyte. I know that there is space on the remote end for a kilobyte of data, so I can send to say, here's a message from me, and by the way, here's the data. Okay. If there's no matching receive, then the data must be buffered at the receiver. But it's called eager because you're very eager to get rid of the data. You basically say, I want to send this data to somebody if it's small enough, and that's called the eager limit, which is typically a few kilobytes of data. You say, okay, it's a small message. I can basically chuck that straight over to the receiver and come back and then carry on my life. Okay. For buffered send, that's obviously a nice thing to do. For synchronous send, you still have to know when it's been received. So you will basically send the data, but when that message is received, so what, if it's a slight technicality, because in your head, eager is like buffered, but you can use it. So if I do synchronous send of a small message, the data will copy directly to the receiver. And then I'll say, well, I need to wait till it's been received. When the receiver receives that, it will send back another message saying I've received it, and then we can. So that will be a. So if sometimes an eager message is just a fire and forget. Sometimes if you've got signals, you have to fire the data and then wait for the acknowledgement. For eager protocol, this requires buffering of the receiving process, and basically this violates the resource semantics. MPI should use a finite amount of memory unless there's a limit. And I'm not going to talk about ready messages here because ready is something you should know. This is why there's a threshold. This is internally, you don't know what that threshold is. It's all vary per implementation, but it's typically 5 or 10K, something like that. So that means that sending short messages, there's a certain threshold at which messages become slower to send. What happens if it's above the eager protocol? Well, they use the rendezvous protocol. So I want to send a message to my neighbor. I look at the MPI library, looks at the data and says, that's too big to use rendezvous, to use eager. So what I'll do is I'll just send a little header message to that guy. When that process picks up the header, it says, oh, there's data from this person, so I'll get back to them, and then you send the data. So an eager message is hopefully just a one-off, fire and forget. If you're using the rendezvous protocol for larger messages, it's a three-way thing. I want to send you data. Yes, I'm ready to receive the data. Here's the data. Okay, it's there. Back. I should have a diagram for this. Sorry. So in some sense, this acts as synchronous send. It waits for the match and receives the messages buffered on the sending process. So this sounds like it's slower. Okay, eager messages, copy it across, rendezvous. I've got some data. Yes, I'm ready for it. Here it is. But for very large messages, it can be faster because if you think about it, you don't need to do any copying. Okay, and copying data is actually quite slow. So with the rendezvous protocol, although there's this initial overhead of setting up things, at some point you're both on the line together, and this receiver could just say, put the data straight into my receive buffer, no internal copying. So there's pros and cons, and hopefully we'll see all this behavior when we run the ping pong example. So typically what you see for MPI performance is that you measure the time against the message size. You will see up to some eager limit, you get a low, then there'll be a jump when it switches protocol to being a different protocol with more latency, more handshaking, and then you'll get a jump, and then you'll get a longer time. So that's typically something you'll see. There's other variants. The short message protocol is like eager, but it's basically, you've got this header. Let's say you've got a fixed 256 byte header. There's probably room on that which is unused. So if I send a message to somebody and it's one double precision number or one integer, I'll send the initial protocol message, which is just the header, but also stick the data on the header. To me, it's like sending a postcard rather than a letter. You know, when you have a letter, you have all the address stuff, and you write half a dozen pages and you stick it in the letter. A postcard, there's so little information. You include it on the header. The postcard has both the header and the data. So what you might see is even shorter time for very small messages, down in the tens of kilobytes range, which is where the message actually fits onto the header, onto the protocol message. There's also DMA, direct memory access protocols, which again allow exchange without direct memory to memory copies over an interconnect without any copying. However, I won't talk about that now. In practice, that hits in for that's only used for such large messages. You very rarely see that. Collectives, as I said, are normally sometimes built on top of MPI point-to-point. In this case, the collection is just library routines. You should never you could re-implement them, but you shouldn't. The optimal algorithms are quite complex and non-intuitive. You want someone else to have optimized it. But as I said before, there's nothing in the API that requires, nothing in MPI that requires collectives to be implemented from point-to-point. For example, modern hardware can have hardware barrier synchronizations or hardware broadcasts. And also, if I do a broadcast in MPI and all the processors are on the same shared memory node, I could just treat it like a shared array and copy the data. But I mean, again, number one optimization in MPI is send a small number of large messages. Number two optimization is always use collectives when you can. There's lots of ways of implementing collectives. If you consider all reduce, you can build a binary tree, for example. There may be ways that this could be optimized. But what your hope is if you do a reduction operation naively, where everybody sends the data to a controller who sends it back, you have of order P messages. On 100 processes, you have 100 messages. A good collective information will hopefully use a log-based algorithm with some kind of tree, which will use significantly fewer steps. So, for example, with a very naive algorithm, to broadcast to 1,000 processes takes 1,000 messages, but with a recursive doubling, like a tree-based algorithm, it's order log 2 of 1,000, and log 2 of 1,000 is 10. So, I mean, I'm not going to go into the details, but basically, you know, typically, collective operations will build some kind of tree and basically send data up and down the tree, merging each point, and that's much more efficient than doing the naive thing. We've talked about groups and communicators. We saw that in that sort of slightly trick question about the all reduce, if you had wanted to have a separate communication, separate all reduce on the even processes and the odd processes, you'd have had to set up 2 communicators. Okay, so logically, communicators are independent communications domains, but in practice, most application codes use a very few communicators at a time. So actually, what MPI does is, in some sense, the communicator information is just like a hidden tag. Yeah, basically, when MPI wants to send a message to a process, it will use its native. Your rank in MPI world is special because it's guaranteed to be unique. So at the very lowest level, MPI will just send data to another process, but to indicate which communicator it's in, there'll be some hidden tag, some number. This is communicator 1, 2, 3, or 4. That's kind of the way it works. So communicators are typically, what I'm trying to say here is, communicators are very powerful, but they're typically implemented in software. They're just a convenient software layer. Process topology, I'll come back to this, and in fact, I actually have some more slides later on. So I'll come back to this later on. Process topology is the way you create, if you've done the introductory MPI course, Cartesian topology, you tell MPI, my processes in COM world are arranged in a 3D grid. I'll cover this more when I come back to neighborhood collectives, because that's where they really come into their own. And we'll talk about the optimizations then in more detail. You may, just to forward flag it, when you create an MPI topology, MPI can't create, you have an optional reorder. You can tell MPI the ranks and the processes in the new communicator must have the same ranks as the processes in the old communicator, or you can say the processes in the new communicator can have different ranks. Might not be obvious why that is useful, but I'll cover that in the neighborhood collective lecture. Single-sided, I've talked about. It is a protocol to allow you to direct writes, remote writes, and remote reads. It's a very complex set of APIs. It's quite ambiguous in some places, and in practice, for many implant applications, single-sided performs slower than point-to-point. The concept they introduced into it for puts and gets is that you declare, when you do send and receive, you explicitly say, here's my send buffer, here's my receive buffer. If you could write directly to another process's memory, there's a worry you could write anywhere and scribble over lots of memory. So MPI+2 single-sided introduced this concept of memory windows. You say this is a window in memory, typically an array, which I'm going to allow people to read and write to. So in fact, the thing which I'm going to cover tomorrow is the MPI3 memory model, which is related to hybrid MPI and MP. And so this window concept is also important there. But I will not be covering puts and gets to any real detail in this course, because for this reason, in practice, I don't think they work that well. The summary, there's many ways of specifying MPI communication. Should I use send, send, bsend? Which one is fastest depending on the implementation? And this is one of the problems. It's very difficult to write a program which is guaranteed to perform well optimally on every hardware or software combination of network, hardware, or library. But what I always say to people is, people say, what's the fastest? Well, I say implement them all and time them. And in fact, I have a benchmark we'll run at the end of today, which does halo swapping in a dozen different ways, and you'll be able to see, which is the quickest. So sorry, I went slightly over time. Are there any questions before I outline the practical? So what I want to do now is I'll try and share the correct. This is what we're going to do, a practical, actual programming practical. So I have the ping pong exercise sheet here, which you can look at. I should be sharing this, apology. So we have a ping pong exercise sheet here. Okay. And what I will do, actually, I don't like doing this for various reasons, but I will do it, is I will share my whole screen. So I'm always slightly nervous about sharing my whole screen because it's very easy to share things that you don't want to, but I will do that right now. Sorry about this, I got myself confused. I'm going to switch in between windows. Okay, I'm going to have to move. Collaborate isn't very good. It tends to share itself. So hopefully that. Okay. So this is the instructions here. I will. I'll see if so we should be able to log on to ARCHER2, and I'll use I'm called TA Rob 170SH at ARCHER2, but hopefully that's a bit weird. Oh, it's 117. Sorry, it's 117, isn't it? Sorry. Yeah. So I've logged in. Hopefully, so are people able to? So I will. That's one of the problems about sharing the screen. You get this into infinity, but so if you're having problems with logging on, this is the we'll solve them here. We can use a screen sharing or something. So please let me know if you're having issues. We can solve that. The next thing is on ARCHER2, you have to run in the /work file system. So I have to cd /work/ I'll copy and paste that. It's slightly annoying, but that's just the way it is. So it's /work/TA117/TA17/ your username. Now I can get the source code for the ARCHER2 example, which is given here. Oops. I should be able to just get that. Let's hope it works. You can download from the website and copy, but it's actually easier to just get directly. And that is taking rather a long time. I don't know why. This worked yesterday. I don't understand why that isn't working, because it worked yesterday. don't know if ARCHER2's gone down. Okay. Okay, finally worked. Yes. Okay, so I don't know what happened there. Is there other people having problems? Yeah, it worked there, Kate. I don't know why it was so slow, but there it is. There. I don't know, and we want to unpack it. It's very old-fashioned. I'm very old-fashioned. I use. It's okay. There's some problem on the work. The work file system is very slow. There was clearly some temporary glitch on the Lustre file system on work. Where are we? We're on work 2. Okay, okay. So you should be able to make. If I do ls, you should be able to make. Yeah, make. But I would edit the make file, the archer2.job, because if you look, we actually want to use these. I've got some. We want to use this. This will run quicker. Okay. So if I use those. Yeah, we want to use this. The reservation is set up for us to. There's some file system problem on work 2. That is unfortunate. This sometimes happens if it's being heavy. That was what the delay is, and see why it's taking a long time to save. I'm sorry about that. I've just hung on here, which is very annoying. There is some problem on work 2, clearly. I don't know if other people are getting. Sorry, yes, I will also. I will. I'm sorry about this. It's just hung for me. That's. Yeah. So I should be able to set up the profile as settings. Where is it? Yes. The way to set the size here. Where is it? Sorry, I'm sorry that isn't. Maybe I can just do. Really able to. There is a way to do it. Settings. I'll fix that. Sorry, apologies. I should be able to get a bigger font, but I'm not able to because I can't remember how to do it in the. I've done it before. I'll find out. So apologies, the font's a bit small at the moment. So sorry about that. I'll fix that. But if we Emacs the, we should not be using partition qs equals short. We should use what we've got from the website here, which is this. Now I should just be able to fbatch archer2.job, and I can look at how the progress is doing sq minus me, and it's running. And it's run. Okay, so that did work for me. I just see if it works for other people. So I have slight difficulty looking at the chat, but I will give me a second. Yeah, I tried. It didn't seem to work. Which is weird. It works. That works in the normal terminal, but not in the. I will try to fix that. There's a setting here. I can't remember where it is. Give me a second. It's under command. Oh, okay. Well, no, it's not really very good, is it? Okay, so what did you have? So what, Martin? Which account are you running as? Are you on a TA117 account or not? Okay, so for your account, you'll need to just you can't use the reservation with your account, but you could use I think you can use the defaults. Well, you can use QS equals short, and that will run quickly, but not as. So you have to use QS equals short and partition equals standard. You'll not be able to use the reservation because the reservation is tied to a particular group, which is the yeah. So you can't. So no, you have to go to you have to CD to. There's two TA17s. It's a double. It's not obviously slash work. If you look at here, it's work T. Is that? Yeah. It's to do with the way that. Yeah. I could. There's a reason for it. I have done this before, but oh, there it is. Okay, so sorry, that's better. Sorry. So is that better? Sorry, it took me a while to get there. So what you'll see if you run it is you get this ping-pong.out, which the important point here is it prints out where they're running. So you'll see here that the way it's set up is that rank 0 and rank 1 are both running on the same node. So this is not using the network. This is using the shared memory on a node. It's shared memory on a node. It's useful. The instructions should all be in here. But I'll just do the module load GNU plot and GNU plot minus persist. It's very old-fashioned to use GNU, I know, but it's just plot time plus GPU is what I like. So there's other things to play around with, but if you look at this, what you'll see is what this is plotting is the time, okay, for standard and synchronous send against message size. Now, this is yeah, okay. I'll try and run it again. It's quite difficult to get. It's quite. That didn't look particularly. I'll run it again. That looks. The data can be noisy. Okay, so I would say on a node, my description of how protocols work was thinking about the general case, which is when data goes between two different nodes over the network. This default case is running on the same node, and that means that actually my statements about what protocols it use may not be correct for ARCHER2. So in fact, you may get rather, yeah, okay. we're getting slightly bizarre. So there's a comment from somebody here, so I was just not keeping up with things. Oh, so it, yeah, there could be an issue. Yeah, you need to use my, with my, there could be an issue with my, it could be an issue in my GNU plot, but I don't think it is. I think it is, you have to, yeah, you have to log in with, you have to SSH. Okay, so or what are you using? What terminal are you using, Martin and David? No, David and Lorenzo. Is it Windows? Ah, oh, so Windows VS Code, I don't know. Okay, fine. For Lorenzo, you'll X Quartz on a Mac. Oops. So Linux should be trivial. Linux should just work. But David, you said Linux, but what? Oh, you're just So Linux, fine. On the Mac, you may need to install X Quartz, which is the X server for. So actually, okay. Okay, that's good. On Macs, there's some weird -y stuff. So what we can get out of this is we can get some idea of the latency. So I think this high number here is possibly a an artifact that the first ping pong is not quite correctly timed. The synchronization might be right. But the most important thing is we're getting how many? 1, 2, 3, 4, 5. We're getting about a microsecond. Okay. So the latency of message passing within a node is about a microsecond, a billionth of a second. That may sound like it's very quick, but remember we're multiple gigahertz. That's many thousands of CPU operations of cycles. So what's the bandwidth? Well, I'll look at the bandwidth. And we'll see that again, it's slightly complicated, but we can see that the bandwidth is going up to about 10 gigabytes per second. That's the sort of number here. There's now, so we get the kind of numbers we'd expect, which is latency of order of microsecond and bandwidth of 10 gigabytes. Those are the kind of numbers I bandied about before. However, on a node, it's doing all kinds of shared memory tricks. So maybe more interesting actually is to do so to run the way to run across. It's mentioned the sheet, but what I would do is to do this. Okay, so that says use 2 nodes, use 128 pass. Well, you could do task per node equals 1 if you want. Actually, you want. It doesn't matter whether you do 228. The ping pong takes place between the lowest numbers and the highest numbers rank. But you could do nodes equals 2 tasks per node is probably the thing you want to do the clean, to do a ping pong between 2, guaranteed to go across the network. So somebody could run that and see what they get. That'd be very interesting. So there's quite a lot of other things but I think the I haven't looked at this for a while. I've been running this exercise on a different system, Cirrus, the last couple of times because of machine unavailability. So we get the right ballpark parameters, a microsecond and 10 gigabytes per second from message passing on a node, but who knows what protocol it's using under the hood? Because it's not using a network. So the actual details of the plot didn't follow what would have been implied with my protocol. However, in a real program, you'll always be running between nodes. So actually, the way that message passing works between nodes is more interesting to an applications program than works on the node. So if someone could maybe, if someone could let me know when. Okay, Camp. So Camp, are you happy to share your screen? I don't know if that's something you'd be happy to do, or well, so I need to make you a co-presenter. So I need to make you a make presenter. So now you should have a share window down here, share content. It's much easier just to share an entire screen, but this is being recorded, so you might not want to do that. I can delete things from the recording if there's an issue, but so you should have a button in the bottom right here, which is share content, which will kick up a window. And I'll stop. Actually, I should stop sharing so I could hear. Okay. Now it says you're sharing. So it says Cameron Wilson is sharing content. We're not seeing anything. I can't see. Although it's. Can you maybe quit and go again? I think it might have been because I'd hijacked the session. Maybe try stop sharing and then resharing. I think I may have messed you up by not quitting. Okay. Oh, you can see. Okay. So I can't see it. That's weird. That is weird. You're saying, Luca, you can see it. That's very strange. I think it must be because I'm the. That's weird. Okay, I'll quit and rejoin. Give me a second. I'll come back in a second. I'll quit and rejoin. That might be an issue. Yeah, it's me. Sorry, it muted me when I rejoined. Sorry. So I was just saying that it's quite hard to. There's clearly three regions here. There's the very short message region here. There's the large message region here. So this is the very short message. These are both eager, but one is using the very short message protocol, and the synchronous send takes longer because there's the extra acknowledgement. When you go bigger than the eager limit, both protocols use the rendezvous, and so basically they're the same. Sorry, wait, apologies, I've said the wrong. Yeah, apologies. I should say the opposite thing. Above the eager limit, standard send becomes synchronous send. Sorry, so they're identical. And then intermediate region, which is the eager limit, but beyond the very small message threshold. The eager limit on ARCHER2 is slightly confusing because ARCHER2 does two things. If you look at the documentation, which I find very confusing, the MPI library in ARCHER2 splits a large message into multiple small messages, each of which could be sent eagerly. So the effective eager limit, if you Google what's the eager limit on Archer, it might say 8K, but the effective eager limit is probably 8 or 16 times longer than that, because actually it will split a message up into maybe 8 or 16 separate pieces. So it's slightly confusing, but hopefully you'll see that we do get, we do see for the internode latency bandwidth plots, we see the general performance model we'd expect, and you can pick out, if you squint hard enough, these different regimes. And nicely, we do see the very short messages regime, which is in the 100 or couple of hundred bytes. You see that drop in latency again. Maybe if we, that's another. So that was really, I'm happy to stay on. So there are quite a few other exercises in the sheet. I'll yeah, you can do. The other thing you could look at is this. That ARCHER2 has a very complicated NUMA cache hierarchy, and in fact, you probably will see quite significant behavior differently between two processes on core 0 and 1, and two processes on core 0 and 128. And you can also, if you look in the code, you can there's a couple of hash if defs which allow you to do buffered or strided send. Another interesting thing to do is to run these on a different platform if you have access to other machines. They're useful characteristics to get a handle on. So that was interesting. Is anyone, if anyone is having, issues logging on, then we can do a screen share to sort it out. It's up to you. I think most people applied for accounts. As I said, if you're using your own account, i.e. not a use partition equals standing QS equals short, that will run in the short queue, and it should run pretty quickly, but not instantaneously because we haven't reserved resources here. And I think that's about it. Are there any questions? Actually, Cameron, I'll just make you back to being a make participant. Ready, quick. I'm happy to. The final thing I'll just look at the sheet. I think it was interesting. We'll look at. So people have been in. Hopefully you can see that. I saw the message. I don't know. So, David, that's a very, I don't know. Why did bandwidth the standard 76% not become equal for high with personal super? I don't know. I mean, the standard, I mean, that, I think I might be making this up. I think it used to on ARCHER2. I think something's changed. Can you remind me which is higher? Which is more performant? Which is quicker? I don't have the graph up just yet. Yeah. So, I mean, there could. Okay, so That's a very good question. I don't know. I don't know what, I'm trying to think what protocol it could be using. So, okay, so the difference on, I'm not answering your question, but the difference on the same node is, yeah, you have the possibility of doing a direct copy from sender to receiver memory, yeah, into the receive buffer, yeah. So so it's possible it's doing some trick where the problem with the ego limit is you need to have a temporary buffer to copy into. That's why it's limited. Yeah, you could say I can't do an arbitrary size method with a direct ego approach because I can't guarantee. But possibly, but no, not for standard sense. Could we do them all synchronously? Well, okay. We can look. What it could be doing is it could be actually making everything synchronous rather than asynchronous and saying to somebody, tell me the memory address of your buffer and I'll just write straight into it. That's all I can think is happening. That's a very good question, Martin. What I'll do is I'll share a different so I'm trying to find the right screen. I'm just so I'm trying to try this, but I've lost my where I. Okay, can you see my screen? Yeah. So if you do man MPI, there's lots of stuff in here. So if you look for stuff like shared memory, let's do GPUs. It's all GPUs. Okay, there we go. Well, here's the thing here. Lots. You'd have to look here. It's a very good question, and I don't understand. I'm not able to answer. What I am able to say is it is the option you have on shared memory, which you don't have in across nodes, is that you could just get another process to say, tell me what's exercise 2. That's the exercise 2 is just what did I do on exercise 2? So I'm too many windows open here. Oh, give me a second. I don't think I get that. That's okay. In fact, I just that's running. Still running. It's taking rather a long time. There's something wrong with the file system. It could just be a delay. I think, Kate, I think it might just be very slow. There's definitely some brownouts on the file system going on. It might be, yeah. But it's taking a long, that shouldn't take that long to run. It's taking a long time to run because it's browning out. Okay, it's finally we're getting, yeah. I think I would try it again. I know that's not very, I think we're hitting, yeah, I would just try again. I think there's file system issues at the moment, unfortunately. Yeah, I think there's, yeah, sorry about that. Okay, so it's up to, so someone asked, it was Martin. No, David, I'll maybe ask the, David Martin, can you send me an email with that question in it? Then I just to remind me, I've got a lot of things to keep my head around, but if you send me an email, I will maybe remind me that I may when I next see the HPE people, I'll maybe ask them. It's a good question. Not what I've expected, but there may be some. As I said, it's something of a moot point because for a real MPI program, you only cared about the slowest thing, which will be the internode comms. Given the but it's interesting. That'd be nice to know what that is. Definitely don't get that behavior on our other system, Cirrus, which is much older though. Anyway, I've got to go and get lunch. But we'll see you again at 2 o'clock.